All right, back for second portion. Where we left off was we're just about to talk about relative motion in 2 dimensions. This is where it gets fun. As an example of introducing, relative motion in 2 dimensions, you can think of a particle we'll call P with two different reference frames, S, and we'll call the other one S prime. This is figure 426 in the book if you want to see a better representation of it than I can have here. But anyway, reference frame S would be where the origin is here, and you have X, Y, and Z axes. Reference frame S prime is at the tip of this the vector R, S, S prime, and you have X prime, Y prime, and Z prime axes there. And so the position of the origin of S prime as measured in S is R, S, S prime. So that is the position of this frame of reference relative to that frame of reference, R, S prime, S. So it's this in relation to this. Position of P as measured in S prime would be R PS prime. Okay, so that's this. So this is point P out here. It's a little obscured by the artwork to use the term loosely. But anyway, the position of P is measured in S prime. So the position of P relative to the origin of S prime is this vector here, R PS prime. So it's the position of P relative to S prime. The position of P as measured in reference frame S would just be R PS. That is the vector that gives the position of P relative to S. And that would be this vector here, RPS. So if we want to find RPS, it's really just a combination of RPS prime, which is this one, this vector here, and RS prime S, and that's this vector here. If we add those together as vectors, then we can find this vector here. And it's kind of a way of finding the position of P relative to this frame of reference by taking the position of P relative to this frame of reference and the position of this frame of reference relative to that frame of reference. Okay, so if you add those two things together, you can find the location of P relative to this frame of reference. So we take RPS is RPS prime plus RS prime S. Notice that the inner terms cancel for the subscripts. And if we do that, then we get what we want. You could do the same thing with the relative velocities. The equations of the velocities would just be the derivative of the position vectors. And so the velocity of P relative to reference frame S would be the velocity of P relative to S prime plus the velocity of S prime relative to S. And again, the inner terms and the subscripts cancel. Okay, you can do that with accelerations also. Acceleration of P relative to S is the acceleration of P relative to S prime plus the acceleration of S prime relative to S. You can extend this equation to any number of frames of references, as I've shown here with like 3 different frames of references. If you have a particle P with a velocity of VPA, that is relative, the velocity of the particle relative to reference frame A, and VPB, that's velocity of the particle relative to reference frame B, and VPC, that's the relative of the particle relative to reference frame C, then you could find VPC simply by taking the velocity of the particle relative to reference frame A plus the velocity of reference frame A relative to reference frame B plus the velocity of reference frame B relative to reference frame C. And notice again, for each pair, the inner designation, the inner letter in the subscripts cancel. So A cancels with A. For the second pairing, B cancels with B. And you end up with P relative to C. Okay. So actually seeing an example of that might be the easier way to do that. For example 13, we've got a truck traveling south at 70 kilometers per hour. Okay, so we could draw a little diagram here. The velocity of the truck heading south is 70 kilometers per hour. And we're going to call that VTE, truck relative to the Earth. They didn't actually say that the Earth was the reference frame, but normally when you're dealing with vehicles traveling down the road, you mean to use the Earth as a reference. So that's kind of assumed. In fact, I think in just about any case, if they don't say what the reference frame is, then you can assume that it's the Earth. Unless they use language like we did in the train example, where you're walking back toward the back of the train at 2 meters per second relative to the train, that tells you that the train is the frame of reference for that speed or that velocity. But in this case, they didn't mention a reference frame, so it's probably safe to assume that the reference frame is the Earth. So velocity of the truck relative to the Earth is 70 kilometers per second south, and a car is traveling east toward the intersection at 80 kilometers per hour. So the velocity of the car relative to the Earth would be 80 kilometers per hour east. And if you draw an actual diagram of this, we would have the velocity of the truck heading south at 70. And if you're going to be really careful about drawing the diagram, you'd want to make sure that the 70 and the 80 are in proportion to each other. And the velocity of the car relative to the Earth is 80 kilometers per hour east. And what we're looking for here, what is the velocity of the car relative to the truck? In this case, that would just be the hypotenuse of this right triangle. And we also want to know the direction of the car, because if we're talking about velocity, we need to know not only what is the magnitude, but what direction is going in. So you have to establish a common frame of reference. In this case, the common frame of reference would be the Earth. The velocity of the car relative to the Earth mathematically would be positive 80 kilometers per hour times unit vector I, because the car is moving in what we normally consider to be the X direction, and it's moving from left to right, which we normally consider to be the positive direction. The velocity of the truck relative to the Earth is going to be minus 70 kilometers per hour times unit vector J, because the truck is moving in what we normally consider to be the Y direction, and it's moving downward or to the south. And we normally consider that to be the negative direction. So that would be negative 70 kilometers per hour times unit vector J. So the velocity of the car relative to the truck is going to be the velocity of the car relative to the Earth. Now, in order to get this to work out so that we have car relative to truck, we need the inner letters on the subscripts to be E. We want Earth to cancel out. So that means we need velocity of the car relative to the Earth plus the velocity of the Earth relative to the truck. The problem is what we've got is the velocity of the truck relative to the Earth. Well, we can switch that around easily enough, because it's just, if you're looking at it from the other point of view, that basically just reverses things. So the velocity of the Earth relative to the truck is just going to be the negative of the velocity of the truck relative to the Earth. So instead of 80 minus 70, it's going to be 80 plus 70, or in other words, 80 minus 70. So it's 80 kilometers per hour times unit vector I plus 70 kilometers per hour times unit vector j. So that is our vector equation for the velocity of the car relative to the truck. If you want to know the magnitude of the velocity of the car relative to the truck, then it's just going to be the square root of the x term squared plus the y term squared. The x term was the 80 kilometers per hour. The y term, I guess, well, actually in this equation, it's positive 70. Doesn't really matter whether you use the positive or the negative in this case, though, because it's going to be squared, and that'll come out the same way either way. And that gives you a relative velocity of the car relative to the truck of 106.3 kilometers per hour. And you'll notice that proportionally, that does look to be, 106.3 seems pretty plausible if that is 80 and if that's 70. I didn't draw the diagram particularly carefully, but it's in the ballpark anyway. Also, the angle, if you want to know the angle that the car is moving relative to the truck, that's going to be the tangent of y over x. And that'll be tangent of 70 over 80. And that comes out to be 41.2 degrees north of east. So in other words, 32 degrees above the x-axis. This is the way we normally measure angles. So you can just use the angle as it is, 41.3 degrees. And in fact, the way I've drawn it, it looks like it probably is right around that, something similar. All right. So that was one example. That was fairly straightforward. A little more complicated is the next one, flying a plane into a wind. Because, well, flying a plane into a wind that's either coming directly from behind you or directly ahead of you, that would be a pretty easy problem because that would essentially just be a one-dimensional problem. But if you're flying a plane into a wind that's hitting the plane at an angle, then it's not only going to, the wind is not only going to change your speed, but it's going to change your direction too. The diagram here gives you a pretty good idea here, what's going on here. If you want the plane to end up going due north at a certain speed, but the wind is blowing from the northeast at a certain other speed, then that wind is going to have the effect of not only slowing you down, but it's going to push you toward the southwest. If the wind is coming from the northeast, that means it's heading toward the southwest. So what that means is that you're actually going to have to set a course for the plane at an angle. It's basically canted a little bit into the direction from which the wind is coming, so that when the wind blows the plane, it'll end up blowing it onto the course that you wanted to take anyway. So you're going to fly in this direction here, and the wind is going to blow you over to this direction. And so that's where I say the initial heading of the plane will be in this direction, but because of the wind blowing on it, it's going to end up going in this direction. Also, because the wind is blowing generally against the direction you're flying, the wind is going to slow you down. So if you want to end up proceeding due north with this velocity, your actual velocity is going to have to be this much greater than that. So we're going to find out what those actual numbers are in this question. The question is, the pilot must fly a plane due north. The plane can fly at 300 kilometers per hour in still air, but the wind is blowing from the northeast at 90 kilometers per hour. So what is the speed of the plane relative to the ground? That would be VPG. And in what direction must the plane be pointed to end up traveling due north when the wind is taken into account? Okay, so as I was saying, in order to fly due north, the plane has to start out somewhat east of north so that the wind will blow it back onto a course that's due north. And remember that when we talk about a northeast wind, whenever we talk about the direction of the wind, we generally talk about the direction that the wind is coming from, because in terms of weather, the direction the wind is coming from tells us more about what the wind is likely to be like than the direction that it's blowing toward. But in plotting out the course of an airplane or something like that, you're going to have to take into account the direction that the wind is blowing to, not so much the direction that it's coming from. And so here we need to be aware that the wind is coming from the northeast, but that means it's pushing the plane to the southwest. Okay, so the velocity of the plane relative to the ground is just the velocity of the plane relative to the air, plus the velocity of the air relative to the ground. Okay, and then we can find the magnitude of the velocity and the direction after that. The velocity of the plane relative to the air, and that's going to be this vector here, is 300 kilometers per hour. And the velocity of the air relative to the ground, the air being the wind in this case, is 90 kilometers per hour. And VPG will just be VPA plus VAG. Notice the A's cancel out and you get VPG out at the end. That is going to be 300 for the velocity of the plane relative to the air. And it's heading, okay, so that's 300 plus for the velocity of the air relative to the ground, we're going to need the y component. And for that, that's going to be the original velocity times the sine of the angle. Okay, and so that's going to be 90 times sine of negative 45. It's negative 45 because it's 45 degrees below the horizontal. Okay, so that's 300 plus minus 63.64, and I end up with 236. The book says 230. I guess that's close enough. I don't know. I'm not sure how they got the 230, but I come up with 236. And anyway, the angle should simply be the tangent to -1. That is the inverse tangent of y over x. And that would be the tangent of the 63.64. That's the y direction over the 300, which would be 12 degrees east of north. And so that is this direction here, 12 degrees east of north. Okay, so that actually does it for this chapter. And I'm going to pause the video for a moment, but I'll continue on with this segment with chapter 5 in just a moment. Okay, for chapter 5, we're going to get into Newton's laws of motion. And this is where we sort of see the background to a lot of the fundamentals of motion and basically cause and effect of what causes changes in motion and why. Okay, so just as a basic introduction, Isaac Newton formulated his laws of motion around, well, actually, his main book that set forth his laws of motion was published 333 years ago in 1687. And his work has stood the test of time. Newton's laws of motion and the equations that he came up with to describe motion are still considered valid today, and they're still used all the time in physics and engineering, which is a pretty impressive feat for a guy who was working 333 years ago with, you know, the level of technology they had in those days, especially since most of his work is based on sort of the fundamentals of physics, and addressing the theory of how forces interact with each other and ignoring such things as like friction and air resistance. So what are just the fundamental forces determining how things move and why? Now, of course, here on Earth, friction and air resistance are things of everyday life. They're always present, and there's really nothing you can do to get rid of them completely. And in Newton's day, they didn't have things like vacuum chambers where you could do your experiments without any air resistance. They didn't have things like space stations where you could go into zero gravity environments and have things be able to move around without friction. And the fact that he was able to envision these relationships between forces and movement and come up with the fundamental laws of how those things relate to each other with the almost total lack of technology that he had at his disposal is especially impressive. As I was saying, Newton's laws are still considered valid and they still apply today. Although one exception is when things get very, very fast or very, very small, Newton's laws start to fall apart. And by very, very fast, I mean like approaching the speed of light, which is incredibly fast, and no physical object has ever actually done that. Basically, light is the only thing we know of that's ever done that. And very, very small, what I mean by that is on the scale of, say, individual atoms or smaller. And that is very, very small. And it's so small that we find it very hard, very hard to investigate or deal with. But anyway, Newton's laws don't apply so well under those circumstances. And that is the basis of relativity and quantum mechanics, which are basically different sets of rules on how forces and motion interact with each other and interact with matter. Those things get so complicated at very high speeds and very small sizes that we still haven't really managed to figure it all out. There are still big parts of relativity and quantum mechanics that are not understood. And even the parts where we do understand what happens, we don't really know why it happens, and we can't really explain the theory behind it all that well. But for this course anyway, we're going to keep things on a normal scale of both size and velocities, and so we won't have to worry about that. If you take general chemistry, we may get into quantum mechanics a little bit, but even there, we don't go into great detail on it. Forces are very important and they're found everywhere. This is why Newton's laws were so important, because you can predict how things are going to react under various forces. Some forces are very large scale and some forces are very small scale. Large scale forces might involve gravity between heavenly objects. Small scale forces could involve, say, the force of an electron zipping around within an atom. Although, as I said, that's a case where Newton's laws wouldn't apply because it's on such a small scale. But small forces can take the form of even something small like pressing on the key of a computer or something like that. Some forces are very well understood and some are not. Some are somewhere in between. Gravity, for instance, it's well understood it's well understood what gravity does. We can predict pretty accurately, very accurately actually, how much gravitational attraction there will be between two objects based on their masses and their distances apart. What we don't understand about gravity is basically why objects with mass are attracted to each other. How does gravitational attraction manifest itself? That's where the mysteries lie. Other forces, like the forces that keep the nuclei of atoms together, they're pretty much a total mystery. So we understand some better than others, some forces better than others. When we're dealing with forces, kinematics have to do with how objects move, and dynamics has more to do with why objects move. So what we've been doing up until now has been more kinematics, but this chapter is going to be more in the realm of dynamics. That's what Newton was interested in. Why do objects move? And that has to do with forces. Okay, that's stuff that I've already said. And if we can sort of come up with a working definition of force, that'll be a good basis of where to start. I wrote in the little haha because one of the definitions of force in physics is something that's capable of doing work. So I thought it was kind of wondering if maybe it was kind of a sly inside physics joke to talk about a working definition of force. But anyway, that's a nerd joke, so you can ignore that if you want. Dynamics are the study of forces that cause movement. And a simple definition of force would be like a push or a pull, particularly a push or a pull that's capable of inducing or stopping or slowing or speeding up movement, or that's capable of doing work. Forces have magnitudes and directions, which means that, of course, forces are vectors. And there's a very wide range of magnitudes of forces. Like I said, the force of somebody pressing down on the key of the computer keyboard is pretty small, while the force of space shuttle taking off, that's pretty big. And forces, I mean, that's not even the total range of forces that are out there. The book goes into a little example at this point about, for one thing, drawing free body diagrams of forces. That is actually an important thing to be able to do because it illustrates how forces relate to each other and how basically what the resulting net force will be. It makes it easier to envision that. And so they have an example of three skaters. Well, I call them three people. So there's person one and person two and person three, but they're ice skaters. So the important thing is here they're on ice skates on ice, so there's very little friction. And one ice skater pushes on the third person going this way horizontally, or actually in 3 dimensions, I guess you would call that the X direction. And the other second skater pushes on the third skater in the Y direction with force F2. And of course, that's going, if they do that simultaneously, then of course, skater 3 is going to go off in this sort of direction here with the total force. But in order to draw that or understand how those forces interact with each other, you might want to put it into X and Y components, where you could draw it like this. Here's F1 from the first skater, and here's F2 from the second skater, and F total will be the resultant, like that. The free body diagram actually just shows, usually shows the object as a point, and the point is normally placed at the center of gravity. That is the center of mass of the object that's being worked on. And the free body diagram usually only shows external forces acting on a body. In this case, the object itself is usually considered the origin. And so, for instance, a force that's pushing on the object would be portrayed as a force sort of originating at the object and pulling it instead. But it has the same effect in terms of physics anyway. So if P3, person 3, is the origin here, then force 1 would be going this way with a certain amount of force, and force 2 would be going that way with a certain amount of force. And that's a simple free body diagram. There are some rules for drawing free body diagrams, and they are, well, some of them I've already mentioned. The object that is being acted upon by external forces is usually represented as a point, and that's ideally located at the object's center of mass. And you treat it as the origin of a coordinate system. And that's why these vectors were going out from that spot instead of pushing into it like they were in the diagram of the actual skaters. Secondly, you include all of the external forces acting on an object, depicted as vectors. and you try to reproduce their directions and magnitudes as accurately as possible. Don't include any forces of the object on the surroundings or the net force on the objects. We'll work that out later. Resolve the forces into X and Y components. In this case, it was easy because the forces were along the X and Y axes, but if they weren't, then you would want to resolve them into the X and Y components. And draw a separate free body diagram for each object if there's more than one object involved in the activity that's being discussed. In most cases that we see, there will be only one object to keep things relatively simple. Okay, so we'll see some examples in the next segment of the video, but I think we're over time right now, so I'm going to stop it here, and I'll be back in a moment.